So we can see how a series integral test works by looking at this this visual here. You can see that we have these series terms. Okay, these bars represent each term of the series, and we can see that as we let n go to infinity, okay, we're just finding essentially the area under the curve. Okay, but you notice the area is a little bit off. So this is how the integral test works. It's basically saying that the integral, this curve, is behaving like the series, like the sequence, and so that if the integral has a finite area, okay, our indefinite integral has a finite area, then the infinite series must also have a finite area. Now we can also kind of prove this as well. Okay, we can see that there is this is a a lower sum, and we can just shift it over and say, well, that's if we start at one more, if we just shift everything one over, we now have an upper sum. Okay, and what we can then say is that, well, if we have an upper sum and a lower sum, okay, and I can zoom out a little bit here. Okay, if we have our upper sum and lower sum, okay, we know that our upper sum is more than the integral, the lower sum is less than the integral, and we know that the integral must be somewhere in there. So we can pinch it in between and say this, right? We know that if we start at 2, we're going to have a sum that's a little bit less. If we start at 1, we're going to have a sum that's a little bit more than what we really wanted. Okay, but if this is a diverging series, this area is infinite. Okay, that means that this must also be infinite, and the only difference between these two terms is just one term. So infinity plus 1 is still infinity. The reverse is still true. Okay, so let's say that this is a converging sum. So this area here is finite. Okay, we know that this area must also be finite. Okay, this sum, infinite sum, must be finite, and this term here is just going to be one bigger. We're just adding one more bar, one more finite value to already finite value. So we know that this must also be finite. So we know that if this is infinite, both sides are going to be infinite. And if we know this is finite, this integral is finite, we know that both sides of this is also finite. So there's a proof of actually why this integral series test actually works. And you can see that they give you actually numerical values here. And we can see that if we let this keep on going, right, this is actually going to be an infinite sum. If it doesn't show up, but it just keeps on going forever. Okay, and this integral will be dependent on. If I change that into some other function, okay, so for example, an x squared function, okay, we can see that this area then changes quite a bit, and as we go to this, we let n go to infinity, right? We can see actually that this integral value is tending towards 1. So the sum is finite. That means that this sum, and this sum must also be finite because they only differ by, in this case it'd be half the original bar, 0.5.